if you imagine a tiny little rain droplet with an incident ray coming at it at some angle, when that ray strikes it, it'll bend differently with its different wavelengths, slightly. And it'll start to spread out into a little bit of a rainbow shape inside that rain droplet. This slightly dispersed light, some of it will refract back out the other side, and it still might not be quite spread out enough for us to observe a rainbow. Could be, could not be. Or it'll bounce off the backside of the rain droplet and start heading back toward the front of it again. At which point it will refract back into the air, and by that point be spread out enough for us to see all the beautiful little colors of the rainbow. And total internal reflection. Here's how it works. It only works when you're traveling from a higher index of refraction to a lower index of refraction. So let's say, for example, I'm shining a laser beam from water out into air. Water has an index of refraction of about 1.33, and air has an index of refraction of about 1. So as I shine my laser beam from underwater up toward the surface, it'll refract, and it'll do so in such a way that when I look at the angle from the 90-degree mark to the surface, I end up with an incoming angle that's smaller than my outgoing angle. And that's simply because my incoming index of refraction is bigger than my outgoing index of refraction. And Snell's law still needs to work. If I change my angle, if I increase theta 1, I'll increase theta 2 as well, the outgoing angle. And eventually I'll get to a point where the laser beam doesn't even leave the water at all. It ends up with what would be a refracted angle of 90 degrees. At this point, my incident angle is known as the critical angle, right where theta 2 equals 90 degrees and does not leave the first surface. At that point, you get no refraction out, you get only reflection.